unfortunately have stopped and Duan from our auto network on here. So in case you don't know, Palo Alto Networks is the largest cybersecurity provider in this world. And so Ruian is a researcher there. His research interest works on the security and privacy of user technologies, including the software security and the networks. He has published 14 papers in the top 4 cybersecurity conference. He has won a lot of awards, and he got his bachelor degree from Tsinghua University and the PhD from Georgia Tech, and he has found multiple CVEs with his research. So without further ado, let's Dr. Ruian Duan to talk.
Yeah, thanks, Professor Gao, for our introduction. And yeah, so my name is Ruian, and I'm here to talk about securing software supply chain. And so this will be the agenda of the today's talk. And I will first introduce some background on what we are doing, and then go from a iterative order of the research that we have done, including from how attackers behave, and then what are the known security risk and legal risk, and what are the zero-day security risk, and also future directions that we know the industry is doing and what we are considering as well. So in modern software development, we have developers who write software that runs on servers or runs on IoT devices. And these software or services are further consumed by end users. But on the other hand, we have these OSS maintainers who write code on GitHub, on GitLab, on Bitbucket, and then they further optionally publish these packages to public registries or package managers, if you call them. And developers, they try to minimize their time when they try to develop some product. So they will reuse these open source packages. And on the other hand, because we have developed this habit of using this packaged software, right? So in this internal process of this software development at corporate, we also have this internal registry, which follows the same CI/CD process as these public repos, but they are just like hidden from the public. They are private registries. And this data is like old, as you see. When I prepared this slides in 2020, there are like 400 million users and 190 million repos on GitHub, which is a lot. I think, if I remember correctly, this may have be increased maybe by 10 times or maybe 5 times over these 5 years. And also back then, the app marketplace was growing, and there was 3 mini apps on Play and Apple Store, and there was 5 mini apps on Docker Hub. And today there is just going to be more. It's not going to be less. And to increase their competitiveness by maybe reducing cost or by reducing time to market, they will reuse OSS for many benefits. However, security risk and legal risk arise. And the first risk that we have is supply chain attack. The cause of this is that publishing to package managers currently has little to no review process. Basically, you and me, everyone can register accounts and then publish a package on these package managers that I listed. And therefore, package managers are being attacked. We have this event stream package, which was compromised, and then in 2 months, 8 million downloads executed against this malicious one, and that means like tens of thousands of potentially affected enterprises. And also, the Docker Hub was backdoored to have those malicious images. And the images that I'm referring to here are those images that was used to mine Bitcoins. And according to the reports, they have earned the criminals 990K back then. Yeah. And this is the timeline of the supply chain attacks which we surveyed in our paper until 2019. And back then there was like over 300 packages that was malicious and over 800 million downloads, which further affects the downstream packages that depend on them, including about 25K dependents. And this how this attack happen? They can be like they can happen due to various factors. For example, attackers can directly publish a typo squatted package so that when we pip install, you can install a malicious one from these attackers. Or your accounts, if it's have a weak password, then it can be hijacked. And they can even like act as a legitimate maintainer, say, okay, you have this package, and I see this package hasn't been updated for 5 years, 2 years. I want to maintain it. Is that okay? Then if you transfer the ownership, then they can immediately turn it into a Bitcoin mining, right? And they can also act as not the account owner, but also as a contributor to your package. Or they can compromise the build infrastructure, which is the case for the SolarWinds attack, if you ever heard about it. And on the other hand, there is a legal risk. So this may not be very very commonly known knowledge, but when you use open source libraries online, it's not like completely free. For example, on the left side, we have the permissive packages in BSD, MIT, meaning like you can do whatever you want, basically. But on the right hand, you have GPL, AGPL. This licenses basically requires that if you are going to make money on the package that some others wrote, then you need to open source your package as well. And GPL is actually a contract according to the US federal judge. And Artifacts has been suing these infringing companies to like comply for their license requirements. And there is also end-day risk. Although the package that we use, when we use it, it may have no vulnerability, but as time goes, researchers or industry, they will find more vulnerabilities. And it's not saying that when you use it, you're not doing good. You're doing good job. But if you don't update it, and when time goes, then it will become vulnerable, and attackers are going to come after it. And this happens for example, Equifax, which is leaked half Americans' social security cards, and also for the community health system, which was abused due to the heartbeat vulnerability. And in addition to that, attackers can also actively hunt for zero-day security risk, which, according to the Google number, has been increasing over the year as well. And as you see, there are like 33 vulnerabilities over this, I think, past 5 years that was focused on enterprise only. And there are like about the same number targeting the end user platform. So both end user and enterprise are at risk for this zero-day security risk. And researchers have been showing that to hack into Apple, you only need a dependency confusion vulnerability. How this happens? Basically, as I mentioned earlier, these big corporates, they have a private registry, and there is a public registry, pipeline, right? Or maybe NPM. And when your private package in your private registry was like not registered in the public one, and your configuration is like not configured correctly, you will try to probe the public one first, and then probe the internal one. So that probe to the public registry can be abused by these researchers or attackers to hack into your system. Basically, you are going to install code from the like a public registry, which you don't want to. And similarly, like for these packages, the account owners may register their accounts, but like as I said earlier, 5 years later, 2 years later, they don't want to maintain this package anymore. But their email account, the domain, may have expired, and then attacker can just take over that domain, and then send a password reset email, and then just take over that account, and then launch this supply chain attack, which is the case for this CTX package, which affects over more than 10 million users and then companies. And so what we have done is on these three dimensions. First, I will introduce my work, my loss, which is published at NDSS 21. This is a framework to study how supply chain attacks work, and then a initial attempt to try to detect these attacks. And on the legal risk and NDA security risk, I will mainly introduce my work OSS Police, which is a system that identifies OSS versions used in mobile apps to identify the legal and security risk. I will not go into detail for the OSS patcher. On the zero-day security risk, I will introduce this CNX package and CNX domain, which covers two patents published already, and they cover the packages that can be potentially claimed by third party or the domains that can be potentially abused by third party. So on the supply chain attack part, as I mentioned earlier, there are many supply chain attacks out there. So our goal here is that to analyze the package management flow and supply chain attacks to understand what's the root cause. And we also want to propose a vetting pipeline to find new malware and also measure existing malware to understand what's the rationale behind this. And in prototype at that time, there was mostly like attacks against PyPy, NPM, Ruby gems. So I just like proposed prototype for this too. I'm aware that after this research, there was attacks against, I think, NuGet, which is the package manager for C#. Yeah. And so this is a typical package management workflow. We have package maintainers who will be writing package on their computer, and then we have contributors, right? As I mentioned earlier, that we try to push code to GitHub, and then these package maintainers will push their package to these registries or package managers. On registries, there are like several components as well. There is an account, which is managing the access to these packages. And there is also the registry. It's just a web server, and the client component on our like a laptop, it's just a pip or the npm binary. And these programs are further consumed by the downstream developers who further write program for end users. How attackers get into this supply chain? Based on our like survey, they can directly publish, as I mentioned earlier. They can also compromise the accounts here, or they can ask them to transfer the account. Or they can like go further upstream to the GitHub repo to say, okay, I want to be a contributor, or I want to, or maybe simply like the existing maintainers, they had a fight, right? And one of them is like not satisfied with the status, and they can like inject malicious code. Or they can like they can actively compromise the infrastructure. And what they're trying to do, they can like steal information from all these like stakeholders, including package managers for their package maintainers, for their like for example npm access code, or developers for their credentials, or end users for their money or whatever, right? Or they can leave a backdoor on these developers or end users to allow them further later come to the website. Whoever was compromised with the malware that they wrote, they can have direct access to those servers. Or they can like try to do some ransomware, or try to delete everything, just anything bad. Or they can like use these developer devices or end user devices as a bit mining computing resources to like make money for them. And they can also use these package maintainers as a way to spread their, just like a worm, how worm works. They can get access to the package maintainers infrastructure, and then get more access to the packages that they control. And how this like happened, why this didn't happen before? Based on our qualitative analysis, we think this is because that previously we, as an ecosystem in the open source security community, we trust the package package maintainers. We trust the developers, but in fact, we shouldn't trust at least all of them. The major stakeholders, we can trust them, but we shouldn't trust all of them. And therefore, we developed this vetting pipeline, which takes packages from these registries and then performs three type of analysis: static analysis, which tries to identify the suspicious behaviors just at code level, dynamic at runtime, or metadata, basically any user correlation or any like a publishing time correlation, right? And then do some analysis. This vetting pipeline has these three components because based on our analysis, we do need these components. For example, as you see in the ESLint scope, in this example, it was actually just fetching code from online and then from the attacker and then running it locally on the compromised machine, which can be like very hard to detect at runtime because as you see, this URL is pastebin.com, which is commonly used domain by legitimate users as well. But statically, we can see this flow from the HTTP content to the eval, which is very suspicious compared to all the legitimate packages. And this Discord user is trying to also request content, but this is just posting content to the to this link. So why I'm putting it here, because it's not directly using the framework API. It's not using npm API. It's directly using another package, which means that in static analysis, you need to analyze the transitive dependencies as well. And the last one is just like a remove everything, and which is not even JavaScript or Python, which means that either you have this cross-language capability or you have runtime detection capability. I'm mentioning all these examples earlier just to help us understand what are the malicious behavior that we're trying to capture. And this is like the actual behaviors or the actual detections that we implemented. We can first look at this graph on the right side, which basically shows that different analysis have different capabilities. By static analysis, we can capture the code generation capability compared to the runtime environment, right? At dynamic, you cannot capture that because dynamic is usually you capture the file system or network activity. And if you don't have that static analysis, then you won't be able to capture the code generation functionalities. On the other hand, because packages may have native extensions, say every package they can have a SO library embedded, or maybe some shell scripts are embedded, which directly talk to the system, and they don't go through the static or Python or Java or Python or JavaScript or Java. Yeah, so that's why we have this combined system to help us increase the coverage. So we analyzed all these packages at that time on each ecosystem, and we were able to detect over 300 new packages that was not previously known. And 3 of these packages was downloaded more than 100K times, which we requested CVEs to help the community remove these effects from these malicious packages. And we did analysis on the behaviors, say what are these attackers trying to do, and we combined the analysis for our packages that we identified, and also for the community identified that we surveyed, as I mentioned in the first half of the talk. And we find that as an attack vector, attackers try to use typo squatting, which is easy. Anyone can do that. But they also use account compromise, which is comparably challenging. but have a higher impact. And in regarding malicious behaviors, they try to steal information, including money, including your secret credentials, or they try to leave a backdoor, which are both very severe. And one new category of attack back then, but now it's not new anymore, is the attack called cryptojacking. Sorry. Basically, I think that was the first attempts in the community that we among the first attempts that we know attackers don't try to steal, don't try to leave a backdoor, but instead try to use these victim machines as a as a Bitcoin mining to make money for them. And transitivity dependency, just we install them and then monitor the request. Just install one package and it. Yeah. So dynamically, not statically. Yeah. In addition to what we have found, we suggested mitigations for different stakeholders, registry maintainers. If possible, they should be implementing a better account protection, right? And also, if they have the capability, I think until now they still don't, they can try to analyze the packages that was published and then see if there are malicious things there. So far that we find is that only this Apple App Store or Google Play App Store, which are financially motivated, they have this incentive or capability to protect this environment. But for this open source package managers, there still lacks incentive and also the expertise to do all these efforts. And for the package maintainers, of course, they should be be more careful about what they're doing and then how many people depend on them, and also be more careful about who is contributing to their repos. Developers, they can just I think be careful. And I said why all this happens. I think it's just somewhere in this whole chain is broken, and then resulting in the end user being jeopardized through these security incidents. And in my loss, what we have done, as I said, is just a very initial early step. But the technology incubated a company from my colleague called Oscillate, and which secured the fund NSF SBIR. And we also opt to share the malicious samples that we identified and also collected from the community, which has been requested by over 140 individuals, organizations, including industry and also and also the academia. Yeah, on the legal risk and the industry security risk, as I mentioned earlier, when we use OSS, although in the first chapter we say, okay, it can be malicious, but even if you are not using a malicious one, it can become to have no vulnerabilities or risk as time goes, right? So one thing that we need to make sure here is that we need to know what is in this app or this software that we have been using. Although maybe it was clear, in nowadays there is something that I will mention earlier called software bill of materials, which is mandated by the U.S. government if you want to do business with U.S. government. But back then it's just nothing like that. So that's this was among the first attempts to understand what was in the app. And in our prototype, we try to propose a scalable system that can identify the loan security risk and legal risk in these apps. And why this problem is challenging? Because there are millions of apps. There are millions of open source software as well, right? So we need to cross comparison. And if you do multiplication, then that's going to be a not a very hard to complete job. And we did our tricks to make this happen. So first, when we want to compare the open source code with these app binaries, one challenge is that what I'm going to extract from these apps and from the source code. Source code is easy, everything is there, right? But apps, you need to understand that what's like remained after you do all this compilation, or this like linking, or this symbol stripping. And also like even if we have these features, even if we have found things that's both present in source code and in binary, but how do we compare? Because like one app is not going to contain only a single open source library. Because otherwise, why do they develop that app, right? It's going to contain the codes from the developer, from open source developer, and from some third party, whatever SDK that they're using. And in addition to this, like component analysis part, we also need to identify the version that was like used in this app, because OpenSSL 1.0, 1.2 is vulnerable, but 1.7, 1.8 they are not going to be vulnerable. So regarding the feature part, what we extract is actually very simple. From the like C++ code part, we have the C source code, C++ source code, right? But in Android apps, which is the scope of this paper, we only have the SO libraries. So SO libraries is just shared libraries that was automatically built by this Android Studio like IDE. And after when they build that, they are going to strip the symbols, meaning that all the Spark, all the debug symbols that when we compile by default are going to present in these like binaries are removed. But what's still there? After analysis, we found that the strings, which is in RO data, and also the dynamic symbols, which is exported functions. So for example, when we use a shell library, you try to like use the print call, right? Or the like system call. Those strings or those exported function names are also in the like shell libraries. So this leads the direction. We basically extract the function name and strings from source code and also from a binary to like do the match. And for Java, we actually have more information. So this thing that we propose here is not new. String as well, like system call as well, but we also like use existing technique which was proposed by previous work. We try to like replace the names by some like fixed strings, such that different after, even if the code is obfuscated at bytecode level, we can still identify them using like their structure. And with the features, as I mentioned, we still need to do the comparison. On the app side, we have like a multiple libraries in the same code, right? On the OS side, we have tons of like open source code. So intuitively, we need to index them. Basically, like we can put the strings functions in a like a Redis database and then map this strings functions to the open source library name, right? This is the intuitive solution, and then this should support the large scale matching. But we find that these two have a very high false positive. Why this happens? Because if we do this, we will have a very high false positive, because open source will have another open source. So like MUPDF is a PDF processing library. This library is going to have OpenJPEG, DeepPNG, and even some whatever names that you you can think of. They will have everything packed in that already. So what we need to do is that we not only need to build this mapping, we need to build a hierarchical mapping, basically from strings functions to the file names, and further to the like directory, and then to the like if there is an intermediate repo, right? When we can then like at that level we can know, okay, this is a software already, and further when we go up, we can know, okay, MUPDF is on top of libpng. So this is like a knowledge base that we built, and then with this we develop our like hierarchical matching algorithm, which is a variant of TF-IDF, to allow us to like do this accurate matching. With this technique, which you can refer to our paper, we analyzed around 100K, more than 100K like OSS versions with 60 from C++ and 777 from Java, and also like 1.6 million apps, which is the total number of the apps in Google Play at that time. Around 500K of them have native libraries, have C code. So this is a finding from us. There are like more than 40K potential GPO violators. Why we see that potential? Because it's very hard. We know they have a GPO component, but we don't know whether they open source or not, because that they can say, okay, we open source at some random corner on this internet, right? So we just report the number and we contact the license holders of this GPO software. Yeah. Yeah. Potential violator, yeah. Yeah, and also there are more violators using C++ than Java, and the majority of these are the majority of these violations are against encoding libraries. And why there are like more C++ violators than Java? We did some further analysis. We find that there is simply more GPO libraries in C++ as well. Java world, they are more open, they use a more passive license. This happens the same for example, Python community or JavaScript community. They mainly use MIT license. But in the C++ world, in particular, Linux is GPO. So yeah, this is what I mentioned earlier. Why they use GPO, AGPO? In C++ world, they don't have an alternative. They either they pay or they use this, they be a violator of the GPO license. And we try to ask like the OSS developers and do they care? So MUPDF donated to Georgia Tech, and some other companies, they either say, okay, we are just a community of developers. We are not a single person. We don't have a copyright or something, so we cannot enforce. This is the response from FFmpeg and VideoLAN. This is also, I think, the response from Linux as well. So there are also copyright infringerators against Linux, but Linux, they try to not like pursue the legal way. They try to encourage the community to share, but they do hold the rights of suing as the last resort. And we also try to contact the app developers, but none of them provide the source code to us. So on the security end, at the time of the publication, there was a Google program called App Security Improvement Program. They try to say, okay, if your app contains a version that Google knows has a vulnerability, then okay, we are not going to let you update your app versions. So by having this analysis, we can then use this side channel to see, okay, does Google have an accurate OSS version detection or not, right? So we basically measured how many of these apps are updated after the deadline. And we do find that this number, more than 1,000, more than around 5,000 of these apps are not detected by ASIP. Basically, they still have this vulnerable OSS version, but they are not captured by Google. So our suspicion is that they use some heuristic or some intuitive method to detect the version, but not a systematic way that we have identified. And another question is that when developers use open source software, are they even aware of this security risk? Based on the analysis on this time scale, we find that it's just random. For some apps, developers will be choosing both old version and new version, likely because maybe they are not directly using this library. They are using this library as a transitive dependency, so they don't even have control over the old dependencies of the latest version that they are using, right? But we do see that some versions, maybe like OpenSSL, they have after the Google enforce this enforce this. These are timelines that ASIP set. And after the deadline, then we do see a decrease in the number of vulnerable apps, which is the red part, decrease over time. And yeah, the impact part, as I mentioned earlier, artifacts are donated to Georgia Tech for findings, although that's for the school. Yeah. And we also received multiple awards. This is me and my colleague doing this Atlanta Startup Battle. And we also get NSF ICOPS to further explore whether this idea is worth commercialization or not. And we also did some follow-up work on this OSS patcher, which tried to fix the vulnerabilities in these apps. And the last part of the talk will be on zero-day security risk. And as I mentioned earlier, there is like two problems that we try to tackle. One is that when we have a package that internal users are using, but also the public registry don't have that package yet. And if they know the name, then they can try to register the package and then intercept or hijack the installation requests. So this basically materialized to a system that identifies the supply chain vulnerability through requests against the claimable non-existent package. How this request can happen? A dependency confusion is a one that was exploited by this researcher. Basically, when we pip install a package, we basically try to follow a as I said, the same installation flow. And why do we follow the same installation flow? Because when we develop internal package, that internal package is going to depend on public package or some other internal package, right? So how to make this happen seamlessly? We just do a pip install with extra index URL. What this means is that we put two registry, both the public pypi.org and also our internal URL at the same same place, and then do iterative check on all of them to see which package is present in which one, so that we can have a same experience as we install a package from pypi, right? Here, when we install a internal package, which may depend on, as I said, internal or external, we can have just this extra index URL to allow this happen. But as I said, this has a risk because we're essentially leaking this internal package request to the public registry as well. Another dummy way is that it can be just typo. Every day we do pip install, we type some random stuff. And also deleted packages, because these developers, they don't maintain a package or whatever, for whatever reason, they delete package. Someone can chime in later, and then if you try to update your CI/CD pipeline, then you will get that package which was already replaced. And so how do we prevent this vulnerability, or how do we identify these vulnerabilities? There are basically two ways. One way is that we can check the URL that they are trying to request, right? The second is we can have a agent that was installed on our laptop, on our machines. And why do we need both? Based on analysis, it's because that different package managers have different ways of requesting packages. For example, for the Ruby gems, Debian, Fedora, all this, or maybe our Ubuntu, they have a way of different stage of updates versus install. So you need to fetch all the metadata to local machine first, and then do the request check against the local disk. So in that way, there is no way that you can figure out this prompt, this probe for the non-existent package, right? But the vulnerability is still there, so we need to check that. For example, someday, the package that we are trying to apt-get, if the attacker gets the package somewhere there, they are still going to compromise our supply chain. Another method is that some package managers, they do per shard fetching instead of per package probing. Why they do that? This is mainly for performance reasons. So they when they try to check if a package exists or not, they are going to fetch do a hash on that package, and then fetch the shard that this hash will fall into, and then check if this package is registered or not. And so for both of these, we cannot observe their behavior at URL level. But for the third type, we can observe at the URL level. But these are the technical details. And uh, regardless of the details, we can think of the simple idea of just checking a URL, right? So in addition to these runtime typos, which we may not be interested in, we need to check those periodically happening errors, or this periodically request of this dependency confusion vulnerabilities. So the idea here is that we check this non-existent package probing request, and we also do a threshold. Just it's not like a fancy machine learning whatever, just a number. If it's over whatever number, we consider it as a important package, right? And then we prevent this request from going to public, and we also try to monitor if anyone try to register this package in the public registry to see if the attack attempt or not. And based on our analysis, we have by checking the firewall logs, as I mentioned, the firewall log only applies to some of the package managers, not all of them. And we already found over 19K for PyPy, and over 23K for NPM vulnerabilities. And out of the top 8 packages ranked by number of requests, 3 of them are dependency confusion, and 5 of them are due to typos. And but on the NPM platform, it's a bit different. Almost all of them are dependency confusion. We still don't know the reason, but that's what we observe. And these are 2 case studies. The first one is a dependency confusion vulnerability from a airline customer. So they basically have I anonymized the name because if anyone knowing the name, they can potentially register the package and then get into their corporate system, right? So they are basically doing this pip install of FTP plan whatever app package, and anyone who can register the package there, they can compromise this supply chain. And the type of scoring vulnerability is interesting. So I don't know if you heard about this subscription manager package. It's a package that was on, I think on Fedora. Yeah, yeah. Oh, that's on Red Hat or Fedora. Yeah, and but when we have a new system, we don't know whether we are on Red Hat or not, right? So we are going to do a apt-get. Is it there? Or pip install, is it there? But then we land on here. However, this behavior, as we know, it can be hijacked by attackers. And the network that I'm introducing here is the CNX domain, which basically it's part of the supply chain risk, but it can also apply to other security risk. So on the at the high level, we consider visiting, if we are trying to visit a claimable domain that's anyone can register. If we see it's an important domain, or if we see a significant amount of traffic towards that domain, then it's already a traffic hijacking or ownership hijacking vulnerability, right? So based on this observation, we basically try to just focus on this claimable domain access parts, and then identify all these requests. We are aware that there are different sources that can generate such NX domain queries. For example, on the name server side, if we have a expired domain, or if we have a typo domain, then this name server configuration will be they're basically just dangling domains. Then they can be generating indirect requests to these claimable domains. Or on the host side, if we have for example, internal network domain that we use, but somehow they become publicly registerable by the attackers, then they can be registered by the attackers to hijack the traffic. And this I think one of the domain here. Yeah. fig leaf. Yeah, I think I mentioned earlier, like the fig leaf domain is the email domain that we know from the maintainer of the CTX, and that domain was used to launch the supply chain attack. So back to the like CX domain, we basically try to identify this high impact claimable and vulnerable non-use domains that can be abused by attackers. And how we can like use these detections, we can basically prevent these NX domain probes from going to the internet, such that they become a secret to the corporate networks, and they are not observable as a public network for any unpassed attackers. And this should allow more time for these vulnerable customers, such that they can like fix the issues or identify the issues. And the fig leaf, as I mentioned, is is the example domain that was like of the package maintainer of CTX. And we also have other like data sources such as Whois, DNS zone file, passive DNS, or our customer data telemetry. And we implement all these like procedures. First, we check whether they have some aggregated number of customers or some number of visits. So I think one difference we need to be aware of is that sometimes industry doesn't need those fancy machine learning or whatever tuning. We just need something that works. So in many places you will see very simple threshold is used, commonly used. And here is what we do. We just like a threshold by number of customer or number of visits. And then we check whether these domains can be registered by third party. And then we try to see how to block, how to provide the protection. And what we found from this system, more than like 2 million vulnerable domains are being visited by our customers. And these domains, over like 10% of them, over 200K or 200K, are persistently being visited. Say persistent being defined as visited for over 10 days. And the number of affected customers is, as I mentioned earlier, like Palo Alto has over 70K corporate customers, and over 60% of them visited persistent vulnerable domain, and over 30% of them visited this domain daily. So somewhere it's broken. Yeah. Yeah.
All those firewall.
Yeah, they're integrated. Yeah, they're integrated in the firewall. Yeah.
From customers.
Yeah, both from customer and from this public source, like a critical domain list, say all the maintainers of PyPy, all the maintainers of NPM. Yeah.
So it's really small. Depends usually it's like you did one customers use the package from public registry, but it's supposed to use internal registry.
Yeah, yeah. Not use, they probe. They do a probe to the public one.
Well,
Probe, they try to like recheck whether public one has a package or not, but we've validated that this package doesn't exist. Yeah, yeah, we block the request. Yeah. Yeah, and on the CX domain case, there are like some interesting findings. The first one was actually like a example like from Cisco Umbrella. That blog actually was, I think, published many years back when I do this system. But I think when I do the slides, I find that their website is offline. I think this is something interesting because when you come solve a problem, you solve the problem, you solve the person who proposed the problem. So basically, this blog is offline, but you can still visit it via archive. So this screenshot is like what I get from archive. Yeah, and this like a claimable X domain can also come from expired domain. Basically, there is a Shopify app that we identify which use a domain, but that app is like discontinued, but anyone who integrates that SDK or integrates that service are still visiting those domains, and their traffic can be hijacked, and then malicious JavaScript can be potentially injected. And the last example is a leaked query from customers' internal domain, which is sncf.cloud. So we identify this domain from like a customer internal network, right? They are being leaked to the public. But I think just this year, a couple months back, we found that this URL, this domain start to host some phishing page, which tries to harvest the as you see, the username or password from the customers. Yeah, that's pretty much what we have done. On the like software supply chain, I think what I want to highlight is that it's a very complex problem. The industry, the academia, we all don't have a solution yet. And on the root cause side, I think basically there is many things that are broken. The account can be compromised, the infrastructure can be compromised, there can be malicious contributors, and there is no package analysis, right? And also the responsibilities among stakeholders. So when something happens, who should be taking action, right? So when we develop an app, there is a software stack. We use an SDK. This SDK's responsibility is that, and that SDK is going to use a cloud provider or their cloud service. Is the cloud service vulnerable? But that cloud service runs on a cloud platform. Is that cloud platform, say they're like a Debian image or whatever image being vulnerable? Yeah. And also, if when we find something vulnerable, who should be like acting, and who has the responsibility, and then do we have a way to fix that, or how do we fix that? We need to make that process easier such that the problem becomes solvable, and then we can start to assign blame or assign responsibility. And future direction, or maybe I think these are not completely future direction, or already actions that has been taken by the industry, by the community. One thing that we noticed that in starting 2020, 2022, yeah, NPM start to enforce two-factor authentication for packages. As I said, industry has this very naive threshold mechanism. If your package has more than 1 million weekly downloads of more than 500 dependencies, they are going to consider it as a mandatory for two-factor authentication. And just this week, PyPy blocked over 800 expired domain email to prevent account takeovers. And on the supply chain integrity side, last month Google introduced this OSS build. So why this works? The idea is that when you have an OSS, right, there are many security risks, but when you have a supply chain, there are many risks. We try to solve one at a time. This supply chain integrity tries to say, okay, if you have your PyPy account compromised, or if you have some like infrastructure compromised, then the build package from your pipeline will become like malicious, right? But if others try to take that package and build their way with a non-infected pipeline, then it should have a benign one. So they can do this cross comparison to see, okay, whether this package is compromised or not. And that is one attempt to like account for example, ideally we should have some package signing, right? But that package signing, in addition to these accounts, everything combined, that's not working. So I think that's a trade-off now. That's noted by Google last month to solve this integrity issue. And also on the package analysis side, the OpenSSF was formed by the Linux Foundation many years back to perform code analysis. And on the transparency side, as I said, when I do OSS police, there is no such thing called a SPOM. But I think in 2020 or 2021, it was introduced by a executive order, and which says, okay, if you want to do business with US government, you need to have this SPOM, which is software bill of materials, to show what components is in your service or in your app or in your device. And on the vulnerability side, there is also attempts that we are aware of, and I also try to actively use, which is, for example, Google tries to dynamically fast all the packages to see if they're vulnerable ones, and also GitHub try to collect the static security-related queries to understand whether there are like common vulnerability patterns that we can avoid when we develop code. But I think still there are open questions. Say basically when we have a supply chain threats, which ones are more important, and then who should be taking action? That's pretty much my talk. Yeah, thank you.
For 2019, some companies got many tax passive open source software ecosystem like passive package and splitting for the companies. Now it is 2025, so recent years, are attackers using any new techniques in about the open source software ecosystem, and have any anti-analysis method you mentioned?
Yeah, so I think the research, we do many research, but the industry or the community actually acts slower. So as you said, in 2019 there are already many attacks, and now there are still many attacks. But one thing that I think I noticed, the countermeasure of PyPy platform is that I think last year, maybe a couple of years back, they took the new account registration functionality offline, so that you can't register new type of scoring packages. Yeah, to answer your question, I think these defenses are still very ad hoc, and as far as I know, they are not very systematic. Yeah, and sometimes when you have a large batch of attacks coming in, they just take the system offline, which is very very naive. Yeah.
Hard those packages in the registry size, especially considering you have consistent dependencies. But it will be much easier approach to build in the firewall because it's basically send everything to the traffic that can monitor traffic. I don't care.
Yeah, I think it's not about easy or not. It's more about financial. In my opinion, it's more about like you need to have a ecosystem that's funded, that's evolving, right? Because Google and Apple, their app store is much more secure, right? And why is that? Because they are making money from that, so they can iteratively improve their expertise and analysis capabilities. Yeah.
Dangerous vulnerability that you found in the wild that raised the most red flags?
I think vulnerability-wise, in terms of dangerous, I don't think it's about dangerous because as you see, any of these CX packages, you just need a package name in the public registry to hack into a airline company, right? And then you can do more things. So in my opinion, all these easy to launch attacks are dangerous attacks, which is just I think essentially we are turning these package names as secrets. If someone from the company leaves the company and go to the dark side, or someone find some clue or they somehow guess the name, then they can hack into these big companies, which happened in the case of Alexa person who hacked into Apple, hacked into Microsoft. Right? Yeah, so I think I wouldn't call it more dangerous. I think it's just how easy if you have the right approach when on the attacker's hand, and then they can easily hack into a very well established companies. Yeah, but that's only the hacking part. We still have a defense in this. I want to emphasize that. So basically, when you try to talk back to the malicious server, or when you try to later maybe access the left the embedded backdoor, maybe there are signals that we can capture. Yeah. Yeah.
Thank you for the presentation.
Hacking security is a constant security issue, and especially when facing very new like technologies like language models like languages. So how can we put our focus on the security issues that caused by this routine?
You mean like there are many security risks, and then what should be our focus? Yeah. Yeah. So I think maybe like first different researchers, different users, different people have different opinions. I can only express my opinion. Yeah. So I think in my opinion, like for security research to like to continue, or for security products to evolve, you need to like you need to make money. You need to like have financial motivation that try to like fuel the system. That's why all this like Linux Foundation, all this like whatever foundation was formed, right? So they try to form a financial like location that can like fuel all this like things that are for the greater being for the like for the general public. And then, but on the research side, I think there is like, as I said, there is for the public research, and I'm doing this like for enterprise research. So in what I think can be focused is more on like what real threats these companies are already facing. Basically, how attackers hacked into the system. Say, one thing that I didn't mention today is the SolarWinds attack. So SolarWinds attack, I'm not sure if you are aware of. It's a like it's an attack that the attacker hacked into the build infrastructure of the SolarWinds company, which is an IT tool, IT management tool development company of like I think over tens of thousands of governments or enterprises. And they hacked into the company, and then they packed their malicious code into a update package such that more than 18,000 companies or like organizations, including the US government, was compromised. So I think we can like focus on basically solving these real attacks, but very challenging attacks, and then see if they can take other alternatives, and then if they and also like why they are not taking those alternatives? Is there like any difference, or they are just like maybe a matter of time? Say like we observe the PyPy, npm, RubyGems being compromised, and then later NuGet is going to be compromised, and even later I think Debian or maybe Fedora are going to be compromised.
Basically, you have this company enterprise focus more on practical.
Yeah.
Threats and
Yeah. All these like real threats, and then how they generalize. Yeah.
Another question? What? Thank you, speak again.
Thank you.
The truth is not much, and